Hi, this is Chris. I still haven't completed the next video about implementing floating point division. That doesn't mean I haven't been doing anything, so I thought it wise to do this short video about one of the things I have been doing. This video covers some much needed code cleanup. When I implemented the logic to perform floating point addition, I used a prefix adder to compute the absolute value of the sum of the two significants. While this works, I always knew the circuit wasn't optimal. One can get much better resource utilization by making a dedicated circuit which computes the absolute value of a signed integer. The adder which was used in the floating point addition circuit was generated using my padder.py script. You may recall that the padder.py script generates prefix adders for addends with an arbitrary number of bits. Starting with the padder.py script, I knew I could implement a similar script to generate Verilog code to compute the absolute value for integers. To begin, I created a new Verilog project to compute the absolute value for 16-bit signed integers. The project only has two files. The first contains the code to implement the absolute value circuit. The second is the test bench for verifying the behavior of the circuit. To create the absolute value circuit, I started by generating a 16-bit adder using the padder.py script. Then I added a wrapper module called abs.py. The module provides the final interface needed for the absolute value circuit. The wrapper takes a single 16-bit integer input and outputs a single 16-bit integer. By way of reminder, the default behavior of the padder.py script is to generate an adder circuit with 3 input values and 2 output values. The first 2 input values are the 2 integers to be added together. The generated circuit refers to these parameters as A and B. The third input value is the carry-in bit. The module generated by padder.py calls this parameter cin. The first output value is the sum of the 3 input values. The final parameter is the carry-out bit cout. You'll need to remember these names as I make changes to the adder circuit. This is the wrapper routine which goes around the adder. Let's walk through what is happening here. The input value in falls into one of 2 different categories. It is either negative or non-negative. If in is non-negative, that is if in is positive or 0, we wish to return the value of in as the out value. If in is negative, we need to return the 2's complement of in. To calculate the 2's complement of n, we start by computing the 1's complement of n, then we add 1. Let's see how the wrapper routine accomplishes this. The first argument to the adder is an exclusive OR expression. The sign bit of the value n is its most significant bit, that is, bit n-1 of n. From the sign bit, we create a bit vector 16 bits wide, an exclusive OR the value n with this bit vector. If n is 0 or positive, the bit vector will be all zeros, and the exclusive OR with the value n is just n itself. The second argument to the adder is 0. The third argument to the adder is the sign bit of n. The adder circuit adds together these 3 values. When n is non-negative, the sum of the value n plus 0 is equal to n. In the case that the input value n is negative, the bit vector, highlighted in the slide, will be filled with 1's. So the exclusive OR argument passed into the adder will be the 1's complement of the input value n. As before, the second argument to the adder is 0, But this time, since the value of n is negative, the sign bit of n, the carry-in value passed to the adder, is 1. The adder then computes the sum of the 1's complement of n plus 0 plus 1 and returns the result in out. Of course, the value of out is the 2's complement of the input value n, and by definition, this is the absolute value of n when n is a negative number. Before diving into the changes which I'm going to make in the adder module, I need to take a moment to review some basic Boolean logic. The adder uses 3 different Boolean operators: or, and exclusive or. When we OR together 2 bits, if one of the bits is always 0, we know the following is true. That is, when one of the input bits is 0, we no longer need to perform the OR operation. We can just use the other input bit value as our result. Similarly, if we AND 2 bits together and one of the bits is always 0, the result of the AND operation will always be 0. Lastly, if we exclusive OR 2 bits together and one of the bits is always 0, then, like the OR case, the result is always just the other input bit. Now it's time for me to go back and clear up a half-truth I told you earlier. I said that the adder circuit used by the wrapper module was generated by padder.py. That's only partly true. The public version of padder.py, which can be downloaded from GitHub, uses 3 utility modules: gij, pij, and sum. The adder, in the first version of the absolute value circuit, was created by a modified version of padder.py, which replaces the invocation of the sum module with inline Verilog code to compute the result. To compute the least significant bit of the sum, the publicly available version of padder.py uses this Verilog statement. The modified version of padder.py uses the following Verilog statement. You'll note that the second version of the computation ignores the input value b. It should be fairly obvious why this is so. b is the second input parameter to the adder module. We know that for this parameter, the wrapper routine passes in a bit vector filled with zeros. So exclusive ORing the value bit b0 into this expression doesn't change the results. So this version of padder.py omits using bits from b when computing the sum. Then I went on to the next change to padder.py. The script was modified to no longer use the utility module gij. As in the case of the utility module sum, the new version of the script outputs inline code rather than invoking a module. For example, to compute g sub 0 colon minus 1, the old version of padder.py output the following line of code. The new version of the script outputs this. The third version of the padder.py script quit using the pij, gij utility module and again used inline code. For example, this single line of code was replaced with these 2 lines of code. The next change was even more modest. I removed the output parameter cout from the list of values returned by the adder circuit. This, of course, also required making a change to the wrapper module abs.py. The next change was to remove the input value b from the parameter list for the adder. We don't really need it because it's always going to be the 0 vector. Above, b was no longer being used in the exclusive OR expressions to compute the sums. However, it's still being used in the computation of g sub I colon I and p sub I colon I values. The old code for initializing the g sub I colon I and p sub I colon I values was the following. Using the Boolean rules which I reviewed above, the old code for initializing g sub I colon I and p sub I colon I is the following. Pay particular attention to the calculation of the g bit vector. Since all of the bits in B are 0, potentially the only non-zero entry in the bit vector g is the cin value. For any other value of I not equal to -1, g sub I colon I is 0. Now we need to revisit the computation of the g sub I colon j values. Looking at the definition of g sub I colon j, we can see that if I equals k, then g sub I colon j is equal to 0, or with the quantity p sub I colon k, ANDed with g sub k minus 1 colon j, and this simplifies to p sub I colon k, ANDed with g sub k minus 1 colon j. Likewise, if k minus 1 equals j, then g sub I colon j is equal to g sub I colon k, or with the quantity p sub I colon k, ANDed with 0, and this simplifies to just g sub I colon k. And finally, if I equals k and k minus 1 equals j, then g sub I colon j equals 0, ordered with the quantity p sub I colon k, ANDed with 0, which reduces to simply being the bit 0. This means that a lot of the g sub I colon j values are 0. Consequently, we can simplify the Verilog code even further. So the next change to the code is to keep track of which g sub I colon j values are 0, and only compute g sub I colon j if it's non-zero. This also means that the only value needed from the g array is g bit minus 1, which of course comes from the cin value. Remember that the wrapper module passes in the sign bit of in to the adder as the cin value, so we can remove cin from the argument list to the adder. Inside the adder, the sign bit of in is the sign bit of a, so we can use bit n minus 1 of a to initialize bit minus 1 of g. The last changes to the logic in the code are a result of moving the exclusive OR operation out of the wrapper module and into the modified adder module. The new version of the adder computes the value of XOR a, which conditionally is either a itself or the one's complement of a. After this, all references to a are replaced by XOR a. Since the exclusive OR operation has been moved into the adder module generated by the modified version of padder.py, the wrapper routine is no longer needed. This also means we no longer need the array p, because the p sub I colon I values come directly from XOR a. Unless I is minus 1, then p sub minus 1 colon minus 1 is 0. I renamed the modified padder.py script to abs.py to match its actual function. The modified script generates circuits to compute the absolute value of arbitrarily wide integer values. The comments and copyright notice were also updated, and that wraps up the development of the script. The next step was to use the abs.py script to update the floating point addition subtraction circuit. I verified that replacing the adder used to compute the absolute value of the significand sum with a module specifically designed to compute the absolute value of the significand sum didn't break the addition-subtraction circuit. Now that the code replaces an adder circuit with a circuit specifically designed to compute the absolute value, let's see what impact this has on the schematic. This is an excerpt of the schematic generated by Vivado for the floating point addition-subtraction circuit. The box on the left is the portion of the circuit which adds the two significants. The box on the right is the new circuit to compute the absolute value of the sum. You can see that the absolute value circuit is a lot simpler than the adder circuit which it replaced and uses fewer FPGA resources. This slide shows the locations of the GitHub repositories with the code changes presented in this video. The first repository is for the new abs.py script. The second is the Verilog code used to verify my code changes while creating the abs.py script. And the final repository is the updated version of the code used to test the floating point addition subtraction circuit using the absolute value circuit generated by abs.py. Hopefully, I can soon find some time to get back to working on the floating point division circuit. But in the interim, I may present some embedded programming projects I've been doing for work. In the meantime, you might think about how to detect an overflow condition from the results of the absolute value circuit. Please share this video with friends and colleagues who might have an interest in this series. Questions and comments are welcome in the comments section. If you found this video useful, please click like below. While you're at it, subscribe to the channel, then click the bell to be notified when new videos are available. Thanks.